Welcome. My name is Ron Papa Schmidt, and I'm the creator of the Net Zero Now YouTube channel. This is going to be video 4 of the relaunched YouTube channel, and today we're going to talk about how do we know calculating global temperature. Now let me put this video into context, okay? When I decided to relaunch the channel, video 1 just sort of described the relaunch, how we create videos and those kinds of things. Video 2 is probably the most important video I'm ever going to create. And it's called What is Our Current Path? The Titanic Table. And in that video, what I did is I went ahead and said, okay, here is what our actual temperature increases have been. And then I also had another section where I talked about what climate scientists say future temperatures are going to be. And I had a third major section that talked about, okay, what happens when we reach those different temperature levels to living conditions here on Earth. And that can be, at times, a fairly stark video. And it also explains the rationale behind my conclusions with regard to how that table works and, to some extent, why I felt that approach in that table was a reasonable presentation of where we're at. But it occurred to me, if I'm doing that a number of people are going to say, okay, why would I believe these numbers? Where do they come from? And things like that. So I decided to create a series of videos to sort of support the information I have in the table. One of those videos is Building the Climate Network. It explains how the major countries around the world cooperatively gather information about what's happening real time in our climate, share that information with each other to do that. And that includes China, Russia, the United States, the European Union, Australia, India, etc., etc., etc. Almost all the major countries of the world participate in this cooperative effort. And all of that is explained in video 3. So the next thing I knew I needed to talk about was, okay, so we say actual temperature is this. How do we get there? How do we actually calculate that actual temperature? Well, when I went to put that together, I thought, well, maybe a good way of doing this, in addition to talking about that, is maybe take one of the world's most sophisticated models and show exactly how they do this. But when I did that, it turned out the video was just way too long. And so I needed to really break it into 2 videos. So I created video 6, which is the Copernicus Climate Model. It's a deep dive into that model. It will walk you through in detail how that model works. And for those that want to really understand more how that works, I highly recommend that video. But it's probably not for everybody. And then this video here, video 4, we're going to talk about now, at a global level, how we actually calculate average temperature. Now, there's a lot of people that are going to say, well, I run into this all the time. Yeah, I don't believe climate temperatures are changing. Well, how do you respond to that? I think the best response is to really say, well, okay, if you don't think they're changing, how do you think we go about calculating a single average global temperature? What is the process for that? What do they do? How do they do that? And I guarantee you, the immediate response is, I don't know. They pull some numbers together. The scientists get together and make up this number, or whatever they want to say, And so this video is going to address that question. It's going to show you exactly how we calculate that. And I think you'll find this to be a very interesting video. So let's begin. Okay, so this is a portion of the table we're going to talk about. We're going to talk about actual temperature increases, how in 2015 we hit 1 degree Celsius, and how in 2024 we hit 1.5 degrees Celsius. And so basically how that happens, in video 3 we talked extensively about the World Meteorological Organization, the organization that collects all this data. But they don't actually calculate average temperature. They just coordinate things. And there basically are 7, what you would call the gold standard, sort of independent calculations of average temperature across the globe. And each one of these institutions sort of uses a lot of the same data, but they have different mathematical models, processing architecture to come up with that conclusion of where we're at. That actually, I think, is a massive benefit because one of them exists in China, one in the European Union, United States, etc. But when they all sort of come up with using different methods with sort of the same answer, that gives you a really good sense of confidence that these results are really, truly what's happening. So let's get into the 7 models. Here are the 7 models, and there are really basically 3 sort of methods that are used. One is the hourly method, and that's what Copernicus does, and that is the most sophisticated approach of all. And they'd use something they call a reanalysis engine. What that does is there's massive amounts of information that's available, but there's always gaps that are going to exist. And by reanalysis engine, what it means is they've gone back and figured out historical relationships between what they see now and what would normally happen in that particular area where they have a gap based on what's happened around it, what's happened from the previous reading they had, and what scientific principles will tell them what happened, and they do that to fill in the gap. That's why it's called the reanalysis engine. And the European model does that for every hour. So basically, for every hour of every day, they basically are doing a calculation that determines what the average temperature is on Earth. Japanese has sort of a similar model. It's not quite as sophisticated. And they run the model every 6 hours. So they do it in 6-hour increments. And then the other 5 remaining approaches use a lot of the same data and techniques, but they sort of create monthly statistical grids. So let me just quickly expose you to the Copernicus model, because if you don't see this, you won't be able to understand what I'm talking about when I talk about a model. And so what you see in front of you is what they do is they measure, if you see these cubes or the matrix or whatever you want to call it above the surface of the Earth, they measure temperature from above the surface into the atmosphere. Now, what they have, if you take a look at it, they have cubes. And those cubes have a horizontal base. And the horizontal base is generally, they try to do it roughly 31 kilometers by 31 kilometers. And so when you do that, you end up with, roughly 540,000 cubes on the surface of the Earth. So the surface of the Earth is broken into 540,000 cubes that are 31 by 31 kilometers in width. And the next thing is these cubes have a vertical height to them. And so they go up into the atmosphere 50 miles, and they actually have 137 layers of these cubes. Now the heights vary. So as you get very close to the Earth's surface, the height is only like 10 meters. Why is that? There's a lot going on the surface of the Earth. I mean, one of the cubes could be in Antarctica, another one in the ocean, on top of a mountain, in a valley, in a desert, etc. And at the surface, you have there's a lot of dramatic activity going on in terms of where it's being temperature changes, rain, other kinds of things. And so as a result of that, they only go 10 meters high. But as you go higher into the atmosphere, you see less variability. And so therefore, the height of the cubes increases. So it becomes very, very high as you get up into the stratosphere. Now, why would they do that? Well, first of all, the information isn't changing much, and by taking that approach, you substantially reduce the total number of cubes, which significantly reduces computer processing power and time and other kinds of things. But when you get through it, here's the interesting thing. With that 137 layers and the 540,000 cubes on the surface of the Earth, you end up with a total number of over 74 million cubes. And each one of those cubes is filled with information, not just temperature information, but other kinds of information that are important. And you can see in the upper right-hand corner here a cube and some of the kinds of informations that are in these cubes. Now they vary somewhat from cube to cube, but they have a lot of information in individual cubes. They'll have things like radiation, wind speed, cloud cover, ocean, heat transfer, all kinds of things that are important for that particular cube or where it's located. Now, the other thing is that from a resolution standpoint, Copernicus basically fills those cubes up every hour and then processes that information and fills it up for the next hour. So that means if you have 24 hours a day, let's say 30 days in a month, you end up with 720 physical snapshots a month of what's happening to temperature. So you have 720 snapshots of over 74 million cubes filled with information relevant to temperature and what's happening in our climate. I mean, that's just basically incomprehensible. I mean, I knew we did a lot before I got into this. Okay, I knew scientists had models and all that. I had no idea the amount of information they have and the sophistication of this whole process and how much global cooperation exists to make sure that this information is accurate and reliable. I'll maybe just give you a sense of the scope here. Here's some of the input areas. These are not all of them by far. I just wanted to show you this. You can see, like, for example, satellites. We have the United States has 14, China 11, Russia 5, European Union 10, Japan 3. All these satellites have a common way of tracking and reporting information into the World Meteorological Organization. They all own their own satellites, but they've agreed to have a set of standards so they can get accurate information around the globe and they can use all this information. The same thing's true for automated land stations, weather balloons, Doppler radar, ocean buoys, etc., etc. Just look at these numbers. And you can see the amount of global cooperation here. And it's over 193, I think, organizations that participate in this. This is just a fraction. But I wanted to show you that even people that theoretically are enemies with one another sort of cooperate to really get accurate climate information. How do they do that? Well, we talked about that in video 3, but they have these various input sources on the left-hand side of the thing here. We saw weather stations, satellites, ships, airplanes, weather balloons, etc. All have transmit information at different intervals that seem appropriate for that particular device and where they are at a particular point in time. Like, for example, airlines will transmit information like every 15 to 20 seconds as they're climbing and descending, but when they're at flying altitude, they basically only report information every 5 to 6 minutes. Anyway. So what you see, all this information goes into national centers. And these input centers basically look at the data, make sure they have it, try to track down information that's missing, or if something, they do some tests to make sure that the numbers look reasonable. Then they pass it on to a regional center, which sort of does the same kinds of data quality kinds of mature. And then they feed the information into this network of supercomputer centers that are located around the world. So we have one in Beijing, one in Moscow, United States, European Union, etc. And all of these supercomputer centers are basically operate real time. So when information enters into one of these centers, it's shared instantly with the other centers around the world. And so they're generally globally available to everybody. Okay, so now let's get into the next segment of this. So when climate scientists talk about temperature changes, they talk about it in terms of anomalies as opposed to real temperatures. So what's an anomaly? It is really the change from the previous measurement period. Let's assume we only did this once a month, okay? If we said the temperature was at the end of June, the average temperature was, I think, let's say in Fahrenheit, about 59 degrees. And then in July, it was 59.1 degrees Fahrenheit. We would say that there's an anomaly of 0.1 degrees Fahrenheit. So the next question is, well, why would anybody do that? Well, one of the reasons is you have a lot of noise going on with regard to temperatures. So, for example, you can be, this could possibly even be in the same cube, but you could be at the top of a mountain, let's say, and the temperature up there could be 30 degrees Fahrenheit. And at the valley below in the mountain, the temperature could be 75 degrees Fahrenheit. Or you could be in the North Pole or at the equator, right? Significantly different temperatures there. Or temperatures can switch between hemispheres. So when it's winter in the northern hemisphere, it's summer in the southern hemisphere. So you have huge variations in temperatures occurring there. Well, what happens by using anomalies is you eliminate all of this noise. So that, let's give the example of the mountain again. So that at the end of June, the mountain temperature was 30 degrees Fahrenheit. And then July, it was 32 degrees Fahrenheit. We would say that we really saw a 2 degrees increase in temperature Fahrenheit for the month of June. And if you're in the valley, if it was 75 at the beginning, the end of June, and at the end of July, it was basically 77 degrees Fahrenheit, you would really have a 2 degrees Fahrenheit increase in temperature, in this case in the month of July. I said the month of June for the mountaintop. I should have said July. But you have a 2 degrees Fahrenheit change there too. So while the temperatures are dramatically different, you can see the change is the same. So by using anomalies, you get rid of a lot of the noise. And so you end up with a truer signal. So what really happens here? So when we go back to the Copernicus model, basically they have, for every hour, they fill in the 74 million cubes of information of temperature differences, and they calculate the anomalies there. And the average, and they do that for every single hour, 24 hours a day, every single day of the year. Massive amount of information. And the other reason to use anomalies is that it makes sense to people. So no matter where you are, if we say, so if the average temperature on Earth is 59 degrees Fahrenheit, and we say, well, we've gone up from 59 degrees Fahrenheit to 59.1 degrees Fahrenheit, somebody who lives near the equator is going to say, well, what do you mean 59? I haven't seen 59 in forever. People who live in Antarctica say, what do you mean 59? Or Alaska, 59 degrees Fahrenheit is an average temperature. And so wherever you are in the globe, this number just doesn't have any meaning to you. Where if on the other hand you say, well, no matter where you are, what's happened is that the average temperature on Earth has gone up by 1.5 degrees Celsius over the last 9 years, since the pre-industrial age, or a half a degree Celsius in the last 9 years, people can relate to that. So that's why they use anomalies. It just simplifies it and takes all the noise out. It makes the number more relatable. Now, the next thing you need to know about temperature is there's sort of three major eras where they sort of set yardsticks or baselines and things like that. One of them is the 1850 rather to 1900. And this is what they call the pre-industrial measurement. This is the measurement that is used by the WMO and IPCC, that's the Intergovernmental Panel on Climate Change from the United Nations. This is what they use to track global climate targets and change. And they said that their original, when they met last time they issued the report or set their goals in 2014, they said the goal was to really, as part of the Paris Climate Accords, was to really limit the increase in temperature to 1.5 degrees Celsius to make sure we didn't exceed that level before 2050. Well, unfortunately, we've done that in 2024, but that's a different presentation. Now, the other thing, these are sort of primitive things, and these temperature yardsticks for this period of time sort of focused on the surface of the Earth. They had land stations there, and then they had ship logs and things that would record temperature and other kinds of statistics. So the next period, then, you get to 1940 rather, and I'll talk about this a little bit more. So what happened here is you start to have weather balloons and other kinds of things going on. We sort of shifted from just measuring what was happening on the surface to focusing on the atmosphere. And then because we're focused on the atmosphere for these more, at this point in time, it's the first time we really had some starting to gather information at this level. This is sort of as far back as the reanalysis models, like the Copernicus model, can reach, because we didn't really have atmospheric related data of any amount, a quantity, before 1940. And then the next period is the 1991 to 2020 segment. And in this area, this is when we started to be able to have a very comprehensive satellite networks and other kinds of things that we were able to get really accurate, significantly more accurate, let's say, information about what's happening in the atmosphere, so we could fill in the grid of 74 million cubes. And so this, they wanted to then set a baseline that reflected that reality, and we'll talk about that a little bit later. So in terms of the 1850 to 1900 grid, here's what the different organizations have come up with what their temperatures are. And you can see they're all pretty close. I mean, it may be vary by a tenth of a degree, a tenth of a percent, but they're generally pretty close. I mean, 13.79 versus 13.73, etc. Now, each one of these is calculated different. They use different information and things like that, and they have certain strengths and weaknesses. And I talked about why their numbers disagree on the right-hand side of this chart. If you're interested, pause the video, look at that. I'm not going to get into that because it's just will take too much time. So next thing, let me talk about the 1940 barrier and what happened here. Well, that's sort of the period of World War II, and even before that, it became evident that the World War was airplanes were going to play, and air forces were going to play a major factor in the outcome of that war. And so you really needed to know what was going on in the atmosphere in order to be able to effectively plan missions and do other kinds of things. So there was a massive sort of demand for very sophisticated atmospheric intelligence. And so there were huge investments made in weather balloons and standardized operations and other kinds of things that could capture what was going on around the globe. Because weather is a universal factor, it affects everybody on the planet, okay? We don't just have weather, stationary weather over each country, okay? And so this information then sort of changed the focus from the surface to the atmosphere, and is sort of the starting point, providing the information for the kinds of models we use today. Now, the 1991 to 2020 thing sort of creates a new baseline. And this baseline is really now based off of the really more sophisticated 3D related kinds of matrix things we have right now. So we've had enough history with that now that they decided it made sense to create a new baseline. Based on the quality of information available, and so they basically have now created this baseline through a universal agreement. This was the segment they were going to use. Now, why? How does that work? Well, one of the things that you get from this is now you're able to go back, and so as you now have information for all of these 74 million cubes, right? So you can go back and measure how things have changed for each one of those cubes. In the Copernicus basis, they do it on an hourly basis. Other people have different size cubes, but you get the idea, okay? And the other thing it does, it then sort of says, okay, we're very comfortable with this number now because we have so much more data. Let us sort of separate reporting then from that to back from 1991 back to 1850. And so we can identify what that is. So it allows you to break that out. Now, we're not that far away from the start of this process because it's only like 5 years ago when this baseline calculation ended. So it's becoming used, it will get used more and more as we're going into the future. But the other thing it does, it allows you to recalibrate your models. Okay, so they'll come up with an EIR6 model. They'll have that out probably another year or so. They've been working on that for a while, and all of these models are constantly being changed. It allows you to go back and do reanalysis to make sure it's working by checking it against prior history and doing other kinds of things. So it's very helpful from that perspective too. And all of this information is basically shared, which also helps with the credibility of all this stuff. So what do the models tell us? So here's what the models say. If you take a look at that, you can see the noise that existed in 1850 through 1900, and you can see as you get to 2025 and over to, actually for 2009, it almost disappears. So the models have come together. Why is that? Well, we have more sophisticated related kinds of information available. And so even though we're using different techniques, we're getting the same results. And the fact that that's being done in different countries with different models, I think adds immensely to the credibility of these numbers. But anyway, you can see what's happened. When I was analyzing that, I found out some interesting information, so I thought I would just pass it along. If you take a look at that chart, you'll see between 1850 and 1940, there really wasn't much of an increase. We said, I think there was just a 0.3 of a degree Celsius increase during that 90-year period. From 1940 to 1975, there was basically no change. Well, how can that be? We had the war, we had all this industrialization going on to support the war, and then after the war, well, it turns out that we were generating so much air pollution at the time, in addition to greenhouse gases, that the reflective impact of the sulfate pollution sort of blocks some of the sunlight from reaching the Earth's surface. And as a result of that, we had less radiant heat going back up into the atmosphere to interact with greenhouse gases. So it basically masked the impact of greenhouse gases during that period. About 1975, we passed some clean air laws in the 70s, and so it took a while as those came into effect. You can see what's happened is that we've gotten rid of some of the reflective things that were blocking sunlight from hitting the surface of the Earth, and all of a sudden the impact of greenhouse gases became obvious in terms of its impact on our temperature. It's no longer being offset. And as a result of that, in not that few decades, we've gone up 1.1 degrees Celsius. And in fact, in the last 9 years, we've gone up 0.5 degree Celsius. So let's sort of wrap this up. So the first thing we notice is what's happened in terms of calculating temperatures. First of all, the amount of information we have has gotten just infinitesimally more information, become more complex. I mean, we're now routinely tracking temperature-based information on an hourly basis over 74 million cubes for every hour of every single day for every month of the year. The other thing that's happening is that we now calculate those anomalies at that level. And we have the technology and tools to let us do that reasonably accurate over all 74 million cubes. And the fact that we share this information across the globe, and that other models are using different techniques to calculate temperature and other kinds of things. It just adds to the overall verification of this number, okay? Because everybody can see everybody else's answers. And so I think that just adds an incredible level of credibility to the numbers the client scientists are reporting this. Let's get to the next page here. So, I mean, right now, we have a number of politicians and special interests and podcasts and other kinds of things that are constantly saying climate change is a hoax, it's a con job, it's a scam, etc. You know, we've just spent a fair amount of time. If you want to get more information, go to video 6. We spent a fair amount of time showing you how this calculation is done. It's done, in the case of Copernicus, on an hourly basis, over 74 million cubes of information they've collected from satellites and other things, from information around the world, from all the major powers of the world and major countries of the world, participating actively to make sure that this information is accurate and correct. And we have independent models run in a variety of different countries using different techniques that come up with the same exact result. Climate change is real. Temperatures are increasing. We're at 1.5 degrees Celsius at the end of 2024. It's just a fact. Now, the one thing you will notice, at least I've noticed, and to mine, I never heard anybody who claims climate change is a hoax or or whatever their particular thing was, talk about the grid of 74 million cubes. They never mention it. They never say, well, what part of this cube is wrong? What information is incorrect? What's wrong with the calculation? They don't mention any of that. Why? Well, it's not because the information isn't available. I mean, everything that Copernicus does, it's available online. You can look at it right now. Look at video 6, so even tell you how to do that. It's shared with everybody around the globe. And if this old man with no climate science background can do this presentation, it's not that tough, folks. You mean to tell me that these major political parties or these major oil companies or whoever else is out there claiming climate change is a hoax, you want to tell me they don't have the resources to go do this? Come on, give me a break. So what else is going on? Well, you're going to have to figure that out for yourself, I think. But I think you can guess. I just want to say one other thing. A number of my good friends believe that climate change is a hoax. And they're intelligent human beings. Okay, it's not that they're stupid or anything. They don't get this. It's just that we live right now in such a media-segregated society that everybody sort of is getting the news that sort of reinforces their existing beliefs. They never get any information about this. I can guarantee you they have never seen anybody talking about the Copernicus model with 74 million cubes. And so I think what I'm trying to do with these videos is say, here, let's share the information so we can come to rational conclusions in terms of what we do next. So let's wrap this up quickly. Here is the Titanic Table. I just wanted to show you the box that shows you the portion that this video is addressing. But always, when you look at this table, look at the last column, because that's what it tells you scientists are telling you is going to happen when we reach these different temperature levels. So let's wrap this up. Conclusion. 1, the Earth has reached 1.5 degrees Celsius in 2024. That is a half a degree increase in the last 9 years. That is an undeniable fact. It is reality. Now, that means we're headed towards a disaster that's going to make living conditions on Earth pretty difficult. And unfortunately, as I'm looking at this, I think that's probably going to affect me in my lifetime. And I'm 83 years old. I hate to think of what it's going to do to my kids and my grandkids and my great-grandchildren. And I guess I would ask you the same question. Let me tell you, this is another fact. The only way, and I mean the only way we're going to solve this problem is we need to get the net zero greenhouse gas emissions, and we need to do that as fast as humanly possible. I don't care how we get there, we just need to get there. Whether that, there's many different avenues for attacking that. I'll do separate videos on that subject. But I'm just saying that we need to get to net zero. And then my other question to you is, so if you've watched this video, what are you going to do about it? Or what are you going to do for yourself, for your kids, for your grandkids, and great-grandkids? I'm telling you, here's some ideas. One is you need to vote in every single election for somebody who believes that climate change is a real problem that we need to address immediately. And you need to vote for people who have the capability to work together with other people around the globe to solve that problem. Because we can't solve it. No individual country can solve this. We share one planet. The other thing you do is subscribe to this video. Tell other people about it. If you rate it and comment, that will help the algorithm. But get involved in other things. And just thank you for spending your time listening to this video. I appreciate it greatly. Please join us for some other videos and have a great day.